The third and final type of nuclear decay that we'll be looking at is a gamma decay. So during a gamma decay, gamma radiation is released. So as you probably remember, gamma rays form part of the electromagnetic spectrum. They're at the very energetic end of the spectrum, with wavelengths much shorter than the wavelength of visible light. During a gamma decay, an excited nucleus emits a gamma ray and drops down to a less excited state. So it's releasing a fair amount of energy. However, it's not releasing particles as such. You can consider photons as particles, but in this case it's not releasing any electrons or any protons, so it's not releasing anything that can cause that nucleus to transmutate. So we're not getting a new type of nucleus formed. We're ending up with the same nucleus but in a less excited state. So this is a little bit like with the electrons in the hydrogen atom, how they could jump between different levels and release photons. In the nucleus, we can have it dropping from an excited state down to a less excited state and releasing a photon as well. In this case, because this is occurring within the nucleus, not within the electrons outside the atom, we have, it turns out, much higher energies involved. So let's have a look at a brief example of using this now. So the question is, a radium-226 nucleus decays, releasing a photon with an energy of 0.186 mega electron volts. Part A, is the radium-226 nucleus transmutated in this process? B, what is the frequency of the emitted photon? And C, what is the wavelength of the transmitted photon? Okay, so part A, in this case the nucleus is just releasing a bit of energy, is not actually being transformed into something else. So no, it remains the same nucleus. Part B, we need to use our formula E is equal to hf, where h is Planck's constant. We've got the energy here, we'll need to convert it into joules to put it in here, and then we can calculate the frequency. So the frequency is equal to E on h, which is equal to 0.186 times 10 to the 6, and then to get it into joules we do it times 1.602 times 10 to the minus 19, and then h, that's Planck's constant, 6.626 times 10 to the minus 34. And so then solving this on the calculator, we get 4.50 times 10 to the 19 hertz. Now part C, what is the wavelength of the transmitted photon? Well, we can use C is equal to f lambda to get this, so lambda is equal to C on f. So that's 3 times 10 to the 8 over the frequency, which is the 4.50 times 10 to the 19. And so solving this on the calculator, we get 6.67 times 10 to the minus 12 meters. So that's a very short wavelength.